This lesson is for section 711. We're going to be working with variation functions. Now our main objective for today is to be able to write an equation for either a direct or an inverse variation function. So the first thing that we're going to have to do is talk about the vocabulary here, and that's to make sure we understand the difference between a direct variation function and an inverse variation function. So in our formal definition for a direct variation function, we say that y varies directly with x if there is some non-zero constant k such that y equals k times x. So let's just break down what this actually is saying. So we have a non-zero constant that we're multiplying x by, okay? Now that non-zero constant could be any real number except for 0, so it could be 0.2, it could be negative 3,000, it could be 2 billion. But as you multiply that value by x, something happens to the y. Okay, so it's the same constant you continue to multiply by x. Now, if you increase x, the y here has to increase as well. If you decrease x, the y will also decrease. So in a direct variation, the reason why it's called direct, as one goes up, the other goes up. As one goes down, the other goes down. So that would be an indication that you have a direct variation function. Now, in terms of a real-world application here, a lot of times you'll hear people say how your education varies directly with your, the amount of money you make. So the more education you have, the more income you make. So as one increases, the other increases. And you could switch this sentence up a little bit and you could say the less educated a person is, the less money they make. So as one goes down, the other goes down. Okay. Now, in an inverse variation function, our definition states that y varies inversely with x if there is some non-zero constant k such that x times y equals k, or if you just solve for y here, y equals k over x. So here we're dividing our constant by that value. Now in this case, as x would increase, then y is going to get smaller because you keep dividing a number here by a larger and larger value. Well, that number, the output, has to be smaller. And if you were to decrease x, then y is going to get bigger, okay? Because if you divide k by a smaller and smaller number, then the output here is going to get larger, okay? So the big idea here is in an inverse variation function, as one value goes up, the other goes down, okay? So here in the real world application, the larger a car's engine, the lower the car's gas mileage. So as the size of the engine increases, its ability to, be efficient with gas decreases. Okay, now that we have a basic understanding of the difference between a direct variation function and an inverse variation function, I'm going to go through these 4 examples here where we're provided some information and we're going to model it with an equation. So in this first example, it says y varies directly with x. Well, we know that that's going to be y equals k times x, where k is just some constant. Okay, that's a direct variation function. Now, the second example says y varies inversely with the square of x. So here it's important that we're not just seeing that it varies inversely with x, but with the square of x. So when we write this, we take k and we divide it by, this time, x squared, not just x. Okay, so in example 3, we have y varies directly with the cube root of x. So I want to make sure I'm using the cube root of x here, and it's going to vary directly. So I have y equals k times that value, which is the cube root of x. Now, fourth example says y varies inversely with the 7th power of x. So this time I'm going to take my constant and divide it by x to the 7th power. Okay. So this question here says, do you notice the difference between directly and inversely? So you're probably recognizing the fact that every time you see the word directly, we multiply that constant k here by our variable. When we see the word inversely, we are taking that constant k and dividing it by our variable. Okay, so that's the main difference. Now we're going to go through and look at some different tables so you can kind of see some examples of direct and indirect variation functions. So we have something called the multiply-multiply property of variation functions, and what that says, if you break it down into words, is that for any variation function, whether it's direct or indirect, when you multiply x by a constant, that's going to multiply y by a constant as well. So let's take a look at this first example, which is a direct variation function. Now I know it's direct variation because I have y equals 2, a constant, times my variable cubed. So out loud I could say this as y varies directly with the cube of x. Okay. I can also tell from the table because as x increases, y also increases. Now what we want to do though is look for the multiply-multiply property. So we're going to look at our x values here, and I notice that if I multiply each of these by 2, I get the next value. Okay. In the y column, I notice that if I multiply 16 times 8, I get 128, and if I multiply 128 by 8, I get 1024. So here I'm seeing that we can multiply x by a constant, which will also multiply y by some constant. So these constants are not the exact same. However, if I look at 8, that is equal to 2 cubed. So that value actually relates back to your original function here, right? I have 2 to the third power, x to the third power. All right, let's keep that in mind now. When we look at the coordinates 2, 16, 4, 128 a little bit closer. All right, so to get from 2 to 4 here, I have to double that. Well, with a direct variation, what happens, because this is x to the third power, now to get from one y value to the other, it's going to increase by that input 2 here to the third power. Okay, so it's increasing by a factor of 2 cubed as opposed to just a factor of 2. So let's use a different point here to kind of further illustrate that idea. Let's say instead of doubling, I tripled the value. Okay, so I triple that x value. Now, the y will increase by a factor of 3 to the third, okay? Because, again, it's going back to this whole idea that this is x cubed. So I would expect that this value ends up being 16 times, 16 times 27, because 3 cubed is 27, okay? So that's what I would expect that to be. Now, I can check that that's actually equivalent to when I plug 6 into my function here. And so I did that already on the calculator. So you can see I multiplied 2 times 6 cubed, right, which is the original function. I get the value 432. But if I also take that point 16 and I simply multiply it by 3 cubed, or 27, I also get the same exact value. Okay, so that's what a direct variation function does. Now I've got another example here of a direct variation function. This time I have 3 times x to the 4th power. So y varies directly with the 4th power of x. Okay, let me erase here. And let's look at those values. Okay, so to get from one x value to the next here, in this table we are multiplying by 2. And if we look at our y values, these are increasing by a factor of 16, right? 3 times 16 is 48, 48 times 16 is 768. So here, if we break down 16, that's actually 2 to the 4th power. Again, it relates back to your original function. Now in our third example, I'm dealing with an indirect variation function because I have a constant divided by my variable. And you can see it in the table as well. As x is increasing here, notice that the y values do not increase, they actually decrease. Okay, so let's make some room here. Now if I look at the x values, my x values, if I multiply by the same constant 3, I get the next x value here. Now in the y column, I notice that if I multiply everything by a factor of 1/9, I get the next y value. If I break down 1/9, that's equal to 1 over 3 squared. Again, it relates back to your original function. So let's say I take our original point, 1, 2, okay, but instead of tripling it, this time I'm going to quadruple the x value, okay? Now if I'm multiplying the x value by a factor of 4, that means in the y value, that's going to decrease this by a factor of 1 over 4 squared. Okay, because of my original function here. So this value I would expect to be 1/16 times 2, which would give me 1/8. Okay, so let's see if that happens when I actually plug in 4 into the function. If I plug in 4 into this function, I have y equals 2 over 4 squared. So I have 2 over 16, which is in fact 1/8. Okay, so again, you're just seeing how the direct and indirect variation functions actually work. So let's start now with our first example where we're going to write an equation for a variation function. Okay, in example 1, we are given 3 different coordinates, and based off of those coordinates, we're supposed to decide the type of function that this is. Now, obviously, we're studying variation functions, so this is going to either be a direct variation function or an inverse variation function. But on your final, you can't just assume that. So remember, you've got ways and methods to, to deciding if it's a quadratic, if it's a linear function, if it's exponential, and so on. Now, this is just one more type of function that we're studying. All right, so if it's going to be a variation function, we want to look for the multiply property. So I'm going to look for any patterns that I see. Now, in the x values, I notice that if I multiply every x value by 3, I get the next value. Okay, so for the x, we multiply by 3. Now, in the y values, these are decreasing. So I go from 300 to 100 to 33 1/3, but these are all decreasing by the same factor of 1/3. So if I multiply the y values by 1/3, so let's write that in there. So for the y, we multiply by 1/3. That's telling me that this is going to be an inverse variation function because as x is increasing, the y values are decreasing. So let's write that in. This is an inverse variation function. And then to answer part B here, when it says what is the general equation of this function, this is where we have to do a little bit more thinking, and this is the hard part, I think, for most students. So we should at least know that for an inverse variation function, we take the constant and we're going to divide it by our variable. But this is where students get confused because they're not sure, is it x squared, is it x cubed? And what you're going to have to do is go back to your original value here, where you're multiplying. You see that you're multiplying by 3, and that changes the y value by a factor of 1/3. This, if you consider that the x value, and the y value then is affected by 1 over x. So in this case here, y equals k over x is going to be the general equation for this function. Now, as we continue to do more problems, I hope this is going to make more sense to you, but just trust me right now that this is the general equation. Now, to find the particular equation for the function, I just don't want to see a k there, right? I need to have a value right there for the k. So we've done this plenty of times in this course. All you do to find an actual value to plug in here is you're going to substitute in parts that you do know. This is just an x, y value here that you can plug in, and you've got plenty of x, y pairs. So let's say you took the point, so let's plug in an x, y pair. Let's plug in the point 8, 300. So now I have 300 equals k over 8, which means that k is equal to 8 times 300, or 2400. Okay, so the particular equation then for the function, you need to not just solve for k, but you need to actually plug k back in to the original general equation. So we have the function y equals 2400 over x. That is the variation function, the inverse variation function that models this particular data. Now, based off of our function here, if x is equal to 36, what is y? I'm just going to plug in 36 for the x value here. And if I simplify, I end up with 200 over 3. Okay, so in part E here, if y equals 235, what is x? This time you're just substituting in y equals 235, and we solve for x, so we're going to multiply by x and then divide by 235. So 2400 divided by 235 is going to give me x, which gives me a really ugly number, 480 over 47. All right, so that's our first example of writing a variation function that turned out to be an inverse variation function. All right, in example 2, I've given 3 coordinates, and we want to decide the type of function that this is based off of these 3 coordinates. So I'm going to look for the multiply property. Now, for the x values, I notice that if I multiply them by 2, I get the next x value. Okay, and in the y value, it's not quite as obvious here because of the decimal, I think, but if you ignore the decimal real quick and just look at it as 32 and 128, to get from one point to the other, you'd have to multiply by a factor of 4. And to get from 128 to 512, you also have to multiply by a factor of 4. So for the y values, I'm multiplying by the same constant, 4. So for y, we are multiplying by a constant 4, which is the same as 2 squared. So this is definitely a variation function because it follows the multiply property. Now we have to decide if it's direct or indirect, and for that one it's pretty easy to do because as x is increasing, the y value here is also increasing. So this is going to be a direct variation function. So we've got, for naming the function, this is direct variation. Now instead of just saying y is equal to kx, because even though that's a direct variation function, it doesn't model the data that we're given. We have to look at our y value. So it's really important that you can rewrite that y value correctly. So since I have an x, that constant here that I'm multiplying by is multiplying by 2, I want to try to relate that over here and rewrite it with the same base. So I have that 2 here squared, which is equal to 4. Okay, so when I write the general equation, again, it's really important. It relates back to this value and how it's related to your original constant as well. But this is not just y equals kx, it's actually y equals kx squared. Okay, so that's the general equation for the function. Now when we find the particular equation of the function, we need to make sure we find the value for k. So we're going to solve for k. So to solve for k, we need to plug in an xy pair because we have a bunch of them. We have 3 different ones that we can plug in so that we can find our k value. So let's plug in the first one, 6, 3.2. It doesn't matter which one you plug in though, I'm just going to pick the first one. So I have 3.2 is equal to k times x squared, or 6 squared, and if I want to solve for k, I need to divide out that 36. So I have k equals 3.2 over 36. Now sometimes the k values are going to get really crazy, especially when you have like word problems and you have the cube root of stuff. So you're going to want to store that in your calculator, especially when you're working through some of your homework problems. Now in this case, I already simplified that in the calculator and it ended up being 4 over 45. All right, so that's the k value. So when you write your particular equation, don't forget you have to plug it in back into your original function here. So I have 4 over 45 times x squared. This is the particular equation to answer part B. Now I'm going to let you try parts C and apparently E here on your own, and then you can check those answers with the key. All right, in the last couple problems here, we're going to deal with application problems. So in example 3, it says the distance an object falls from rest varies directly with the square of the time it falls. So this is important. It varies directly with the square of the time it falls if you ignore air resistance. Now it gives you some more information here. It says a ball falls 144 feet in 3 seconds. We're supposed to find how far that ball will fall in only 7 seconds. So let's begin by defining our variables. Now the way that this problem is worded helps you a lot because here it says the distance varies directly with the square of time. So remember, thinking back to our examples, it reads usually as y varies either directly or inversely with x, right? So in this case, our dependent variable is going to be distance, so that's like the y variable. You can obviously label y equals distance and x equals time in this case, but I'm going to use d and t just so you guys get used to seeing some stuff. When you start dealing with your homework questions, I think it's easier if you just call the variable whatever it's supposed to represent. So d equals distance and t equals time, and we have the coordinate t comma d. Okay. All right. Now, the fact that they tell you directly how it varies, it helps you a lot too. Distance varies directly with the square of time. So we have distance varying directly, so I have some constant k, with the square of time, so t squared. So this is the general equation. Now to find the particular equation, I'm going to use the information that they gave us in the beginning of the problem here, or I guess in the second sentence, which says that the ball falls 144 feet in 3 seconds. So this is an ordered pair here. Now make sure you write the ordered pair in the correct order. This is the ordered pair 3, 144, not 144, 3. So just be really careful and just always relate back to how you define your variables. So we're going to plug in the point 3, 144. So I have 144 equals k times 3 squared. So I need to solve for k here by dividing by 9. So 144 over 9 is k. So k is equal to 16, which means I have the particular equation d equals 16 times t squared. Okay. Now, with that equation, I'm going to answer the question, how far will the ball fall in 7 seconds? So in this case, t is equal to 7. We're going to plug that right in. Okay. So that's something that you can just type, I guess, right into your calculator, 16 times 49. And for the final problem of the lesson, we have the bomb blast problem. Okay, it says the radiation dose you receive from a nuclear bomb blast is inversely proportional to the square of your distance from ground zero where the bomb goes off. Now I didn't use this specific terminology in our previous problems, but when you see something like this where it says it's inversely proportional, that is the same as if it were to say that it varies inversely. Okay, so if you see something that says it varies directly, then that means the same as if it were to say it's directly proportional. Okay? All right, now I think this problem is intuitive because what this is saying is that here's the bomb, right? The closer you are to that bomb, the higher the radiation dose is. So the smaller the distance, okay, the higher the radiation. So if you increase your distance from the bomb, so you're out here, then you're going to have a smaller radiation dose. So that's why it's definitely an inverse variation function, okay? Now, we're supposed to write the particular equation that expresses dose in terms of distance. So here, it's not going to be easy to define our variables using d and d, because that'll be repetitive and we won't be able to tell the difference. So I'm going to go back to the whole x, y thing. It's yelling at us. Make sure you don't forget to define your variables. It's really important. You'll lose points and stuff on your test. So let's make x equal the distance you are from the bomb. And that's kind of counterintuitive to what we normally make x and y. Usually distance is not an independent variable, but in this case it is. So x is the distance from the bomb, while y is the amount of radiation. So the amount or dose of radiation. Now we have a coordinate here because it says at 3 kilometers the dose is 400 units. So we have 3 comma 400. Now to set up the general equation, I'm going to go back to the original wording of the problem. It says the dose you receive is inversely proportional to the square of your distance. So I'm going to take the dose, which is y, and that's inversely proportional. So I have k over my variable, and the variable here is not just x, but the square of x, the square of your distance. So k over x squared equals y is going to be the general equation. Now I need to find the actual k value, and I'm going to do that by plugging in the coordinate 3, 400. So I have 400 is equal to k over 3 squared. So then to solve for k here, I multiply by 9 and I get k equals 3600. Now this is not the final, product here, because I want to write the particular equation by plugging that k value back in. So my particular equation is 3600 over x squared. Now using that, we can answer some of these questions here. So I'm going to let you guys do part B here to find the dose that you get at 6 kilometers away from the bomb and 13 kilometers away from the bomb. So remember that as the x value increases, then the y value should decrease. So the farther away you are from that bomb, the less of a dose of radiation you're going to receive. Now for part C, it says if the lethal dose is 1,000 units, how far must you be from ground zero in order to survive? So in this case, we are plugging in y equals 1,000 into the function, and we're solving for x. So we have 1,000 equals 3,600 over x squared. So if I solve for x squared, I'd multiply by x squared first, and then I divide out that 1,000. So I have 3,600 over 1,000. So I have x squared equaling 3.6. Now if I solve for x and take the square root, obviously we do get 2 solutions, but we can throw out the negative because the distance can't be negative. But we end up with a value that's approximately, so let me use the approximate symbols here, 1.89 kilometers away. So you need to be about 2 kilometers away or more in order to survive that blast. All right, that's the end of the lesson. Just remember that variation functions can be tricky. The key is to make sure you're looking at the constant that you're multiplying by in the x value so that you can compare that to the constant that you're multiplying in your y values. Okay? Anyhow, that's the end. Nice job. I'll see you guys tomorrow.